All right, good morning, everyone. Welcome back. So today, I apologize in advance. This might not be the cleanest session. I didn't have as much time to prepare as I normally do. I had a meeting before this, which is why I was a little late. So let's start off today. We're going to begin by continuing where we left off the last time, which is looking at the processor manager class and actually trying to go through all the details of how some of the Legion scheduling works. So just to refresh your memory from last time, we have a couple of different kinds of resource managers. We have memory managers, we have message managers, we have processor managers, and we use these as sort of runtime utility services that all of our different operations are going to use as part of their execution. And so one of the things that we looked at the last time was we looked at memory managers and message managers, which allow us to send messages between nodes, and then memory managers for tracking resource usage. And then we have processor managers on each of our nodes for tracking how busy our low-level runtime processors are for each of our different application level processors. So I want to jump back in to runtime.cc, which is where we have our processor manager implementation that we were looking at the last time. So if you recall, I'm going to jump back to where we were last time just to start off. So we have these processor managers. And I think the last time we were looking at add to local queue, add to local ready queue, which was this method that we were looking at the last time, which is all of our non-task operations come through this queue whenever they're ready to actually go through their mapping process and actually be scheduled. And so you remember that what we're doing is we're adding these to lists of chains of operations that we are scheduling onto our utility processor to actually perform the mapping for these operations so they could actually run. And so today what I want to do is look at the separate path. What you're going to notice is that we have a separate path for tasks, for operations that are actually tasks and not just inline mappings or region-to-region copies or any of the other kinds of operations. So tasks are effectively a special kind of operation, and they get some special treatment inside this processor manager because the main thing that differentiates them is that, well, I guess there are two things that are differentiating about them. One is that they have slightly different mapping semantics. And the second thing is that they can actually be moved around between nodes. So if you remember, most of our operations that we launch with inside of a context tend to stay within a single node. So once we launch them, they're going to run on this node, and we can run them on our local utility processor, and they're not going to be moved around. However, for those of you that have written Legion programs, you know that Legion mappers have the ability to send tasks to other nodes. And so we have a separate path for tasks that they go through, which allows us to have a little bit more, we have to know a little bit more about them so that we can possibly handle mapper requests a little differently and possibly send tasks to other nodes and so forth. So what I want to do is actually walk through that task path today, since we walked through the operation path the last time, and actually see how the scheduler works with this processor manager. Okay, so we know that our operations come through this add to local ready queue, and we haven't actually looked at tasks in a lot of detail yet, but effectively the tasks have a similar call that they can add themselves to the list of operations that are ready to be mapped, and this call is called add to ready queue. And you'll notice that unlike add to local queue here, add to ready queue takes a task op, which is the generic kind of, which is the base class for all kinds of tasks. So this can be any kind of task that we're getting here. It could be an individual task, it could be an index-based task, or so forth. And we'll look at all those different kinds of tasks a later point in time. But really what we're just getting here is a generic task operation. And then we get the same flag that says whether or not we failed to map this task at an earlier point in time. Okay, so we do a couple of little bit of bookkeeping operations here on this task before we put it on our ready queue. But effectively, we're going to do very much the same thing that we did the last time. We're going to do something a little different than we did for operations, but it's going to be sort of similar. What you're going to notice is that we have these ready queue queues that we use for tracking all of the different tasks that are ready to map with inside of a given context. So unlike the operations, notice the operations, we tended to launch those right down on the utility processors so that they can start mapping and running whenever they want to. Unlike those operations where we know we can map them as soon as they're ready to map, the tasks actually have a different semantics. And that is that we want to give mappers the opportunity to choose when tasks get mapped. And the reason for that is they might choose to to defer mapping in order to do dynamic load balancing, such as task stealing, or possibly choosing at a later point in time to send them away to another node. And so what we want to do is actually maintain a queue of all of the, or really the list of all of the tasks which are ready to map for a given context, and then allow the mappers themselves to choose when they want to actually map those tasks. So we're not going to just launch these mapping operations onto the low-level runtime utility processors like we do right away. So instead what we do is we keep these ready queue data structures. And you'll notice that these are being indexed not by context ID, but by mapping ID. So this map ID, for those of you that have written Legion programs, you'll know that for all tasks, when you launch a task, you give it a mapper ID, which says which mapper is responsible for actually mapping this task. And what we're doing is we're keeping a different ready queue available for each one of our mappers to tell it all of the tasks that are ready to map for this particular processor. And so, and you can see, really we keep some ordering on these queues just to make it easy for mappers to reason about what order these tasks were ready to map in. So if we had a previous failure, we actually put it on the front of the queue. And if we didn't, then we just put it on the back of the queue. So mappers know that things closer to the front of the queue tend to be higher priority. They've been in the queue longer, or they already failed or something. Whereas if they're brand new, then we're going to put them on the back of the queue. Just to show you where this declaration is of this ready queue, just so we can see what it looks like. I'm jumping back to runtime.h. I'm going into class processor manager. If we scroll down here a little bit, we find all our data structures for this processor manager. And if we look for the ready queues, here we see that what we have here is a vector of lists containing task ops. So this vector is indexed by your mapper ID, and then you have a list of all the different task operations. And we're going to see that what we're going to actually end up doing is passing a reference to this list to the mappers to allow them to say which tasks they want to schedule. Okay, so let's jump back here. We'll jump back to runtime.cc. Back to processor manager. Add to ready queue. There we go. Right, so you can see these ready queues are being indexed by the task mapper ID. Note before we put the task in the queue, one of the things we do is we mark schedule to false, which is one of the fields on this task, which allows us to know whether or not the mapper has selected this task for scheduling. And so really what we're doing is we're just clearing that field before we put it on here so we don't get confused at a later point in time. Okay, so we build up our ready queues, keeping track of which tasks are ready to map for each of our different mappers. We have to do one more thing here, and that is what we want to do is we want to have some way of knowing how far ahead to run for the Legion runtime. For the Legion runtime to run ahead as part of its mapping into the future process. And this is controlled by a couple of different parameters. And part of it is mapper controlled or most of it is mapper directed. But what we want to do is maintain some sort of information about whether or not we want to continue running effectively our scheduler. And so we're going to keep track of some state here to actually track whether or not we want to continue launching our scheduler to keep mapping into the future, or keep, at least having pulling the mappers to see if they want to continue mapping tasks and mapping into the future. And there's a way that the mappers control this, and that is the mappers get to say for each of their for each context, we get to say how many outstanding tasks we want to have mapped in advance of where our actual execution is taking place. Let me, just to refresh your memory, I want to show you the mapper calls that we're talking about here, just so we can be very concrete about this. So I'm going to jump back to legion.h, which is our main interface. I'm going to search for class mapper. Here's our mapper class. I'm going to find the right runtime call here. I think it is select context, or select here. Was it select task options? No, it's not select task options. Let me find the right mapper call here. Here we go. Configure context. So one of these calls, whenever we start a task on a node or running on a processor somewhere, one of the first calls that we do is we ask our mapper that's responsible for mapping that task to configure this context. And what you can see is there's a couple of different parameters here that they can set on your task object to control, the execution, how far ahead we're going to run for this particular task. So if this task launched any subtasks or sub operations, how far in advance do we want to actually run in order to hide latency and stuff like that? And so one of the things you can control, for example, is the max window size, which is how many outstanding operations you have inside of this task. But the other thing that you can set is this parameter here, this min task to schedule. And what this says is how many pending operations do we want to have mapped, or subtasks do we want to have mapped inside of this parent task as part of its running before we stop asking the mapper to continue mapping. And the reason for having this is that we want to run into the future, but we don't want to run too far into the future. And if we run too far in the future, we just keep failing mappings, then we just keep pinging on the map, pounding on the map, or asking it to remap stuff, and then it tries to remap, and then it fails, and we get in this nasty feedback loop, and we end up burning a lot of cycles that are unnecessary. So what we want to do is sort of give mappers a way to help scope how far they run into the future. And so one way of doing that is controlling this minimum number of tasks to schedule. And that's sort of, and we make this a mapper call so that mappers can configure this parameter separately for every single one of our different tasks that we're running. And controlling the minimum number of tasks to have outstanding that have mapped inside of our context is one way to control how far in advance we are. There's other ways of doing this that we also support. One of the other ways that you can do this is you can launch frame operations if your application launches frame operations to sort of demarcate sets of operations, then you can say how many frames you want to have outstanding instead of the number of tasks that you want to have outstanding that are mapped. So for example, you can there's a way to mark off or issue frames around, say, a time step of your simulation. And then this gives the mapper a much clearer way of describing, I would like to be 2 time steps ahead or 3 time steps ahead of my particular current execution. And so that's a cleaner way to do it if your application is if you're actually willing to take the time to put those kind of markers into your application. However, for the default, we'll just look at this min task to schedule case today because it's the base one and it's the one that's most common for most applications today. Okay, so we know that we have this min task to schedule. Let's see how that's actually used inside of these contexts. So I'm going to jump back to runtime.cc here. And we're going to look at this state update call that goes on inside of add to ready queue here. Back to add to ready queue. Okay, so what you're going to see here is that we have this context state object. And the idea of this context state object is that it actually marks, it's actually tracking how many, whether or not the state of this context, and when I say context, what I really mean is the parent task that this task was issued in. We're tracking whether or not it's active, and then we track how many outstanding tasks we have that are ready to actually be run. Okay, so the state.active field, first off to tell you, we'll say that a state is active as long as it doesn't have enough outstanding mapped tasks, and we'll see how that gets set in just a minute. And then the other thing that we check is that we check whether or not we have any owned tasks, which means do we have any tasks mapped but we haven't actually mapped them yet. So effectively, what is the size of our ready queue? We're just really just mirroring that in this own tasks context. And actually, this is the distinction: is that these ready queues are tracked per mapper and not per context. And the state object is tracking how many tasks are ready to map within this context. And so what we're doing is we want to see whether or not so this test here is actually checking to see whether or not we want to enable our scheduler because suddenly we have a new active context, which is ready to be run. So in the case where we don't have enough outstanding map tasks, which is what this active parameter is saying, and suddenly we initially didn't have any owned tasks, but now we're about to have one, then in which case we're actually ready to turn on our scheduler, we can increment the number of active contexts that this processor manager is managing. So let's actually go look at this increment active context because you're going to see the implication that it has. And then we'll go back and look at how we set each of these different well, we can see how own tasks get updated here. We'll see how state.active gets updated in just a minute. But let's actually go look at increment active context. Okay, so this processor manager is tracking how many contexts it has that are what we call active, which means they don't have enough map tasks, so they need to do mapping. And then they don't have enough map tasks, but they have some tasks that are ready to be mapped. So we want to actually run the mapper calls to actually ask those mappers if they're ready to map those tasks. So what we do is we have we check to see whether or not we have any active contexts. And if the answer is we didn't have any before, and our scheduler task is not enabled, then we want to turn it on. And so enable it and then increment our total number of active contexts. And these are tasks, parent tasks that effectively have outstanding children, and we're ready to actually call the mapper to map those outstanding child tasks. You'll note there's a mirrored call here for decrementing the number of active contexts. And that will happen in any number of cases where either our total number of map tasks for our context goes to 0, or our parent task actually finishes and we actually end up decrementing that tasks. One of the important details here is this call here to launch task scheduler. And let's actually see what that does. So I'm going to unwind this. I know I'm pushing a lot of things onto the stack, but I'm going to unwind it here eventually. So in the case where we didn't have any active context before, and our scheduler wasn't enabled, we've now enabled our scheduler, and then we actually want to launch our scheduler to actually tell it to start doing this mapping. And the scheduler is actually, it's a little bit of a misnomer, and I'll tell you why in just a minute. But it's actually a very simple idea. So here's the launch task scheduler. It's a very simple call. Notice we are using one of our high-level runtime meta tasks here. We've got our little HLR ID. We're saying this is the scheduler ID, and this is our local processor. And then on our utility processor, we're spawning our scheduler call. And the idea here is that the scheduler is actually just going to launch a new little meta tasks onto our low-level runtime utility processor. And that scheduler call is going to come back around and invoke something on this processor manager. So let's actually see what that does. So if I search for HLR scheduler ID, we'll find out where this is called. Okay, here's our high-level runtime meta task handler. We do our switch on all our high-level runtime meta task IDs. High-level runtime scheduler ID is the first one on the list here. And so what you see is we pop out of our scheduler args. We get our runtime, and we end up calling process schedule request, and we pass the processor that we want to actually do the scheduling on. So if we search for process schedule requests, we come into here into our high-level runtime. We get our processor. There's a lot of logging that's going on here, but really it's all pretty simple stuff. Most of these are if-def out in most common cases. And really the only two lines of code that are really being executed here are these two. So we're getting our processor manager out of the set of processor managers, and then we're calling perform schedule. So let's look at perform scheduling. Notice we're going back into our processor manager class. So really all we were doing is deferring an operation onto our processor manager. And actually, what was I searching for? I was searching for, we were in process schedule requests. I was searching for perform scheduling. Okay. And here you can see perform scheduling is really a very simple call at the surface. All we're going to do is we're going to perform our mapping operations, and then we're going to retake our lock, which protects our queue of all of our tasks that are ready to map. This protects the ready queue data structure, this queue lock. Actually, I should have pointed that out earlier. We'll see it again later. This queue lock protects our ready queue data structure and all of the associated state with deciding whether or not we want the scheduler to be enabled. And so we perform all our mapping operations, and then we're going to go test to see whether or not we want to keep our scheduler enabled. And if we don't want to keep it, if it's not already enabled, or if we don't want to keep it enabled, then we can turn it off. Otherwise, we're going to launch our next task scheduler. So notice there's, here our test is a little bit different. As long as we still have outstanding active contexts and we're not trying to be shut down by the runtime, then we're always going to launch our next iteration of our scheduler. So we keep calling the scheduler as long as we have contexts which have tasks which are ready to map and we haven't mapped too far into the future. And so that's effectively the condition by which the high-level runtime keeps, launching application-level stuff down onto the low-level runtime. And you can sort of think of it as sort of a, we try to get far enough ahead, and then the application starts to catch up, and then we invoking our scheduler again to get farther ahead. And so really, this is just a feedback loop that's allowing us to control how far in advance we're going to be mapping into the future. And really, the mappers get to control how far we're mapping in the future by controlling effectively when each context can be considered active and not. And as long as we have active contexts, we're going to keep trying to map those contexts into the future. Okay, let's actually unwind this stack a little bit. Let's jump back to where we actually invoke this scheduler. So if we come back here to add to ready queue, recall that we were actually tracking some of this state information for our own tasks. And what we can actually see is we want to look very briefly at how we modify these different state fields of this context just to control how these different variables get updated. So let's actually jump back to where we were at increment active contexts. So you notice that we have these increment and decrement active contexts. There's some other calls up here which actually tell us when to activate our actual context. This is where we're actually setting the state value for each of these different contexts. And these calls actually come from the context themselves. And so what the contexts themselves, remember, contexts are really just single task stars, marking, which context, saying that these are, the enclosing parent task that's launching sub operations. And so whenever we get one of these active context calls, they're actually coming directly from these single task contexts. And they're done whenever we actually end up starting to run a task. And then we can decrement, or then we can deactivate them once we're done actually running that task. And so that controls whether or not this state active is true or state active is false variables. The other cool thing that these calls can actually be done at is if these contexts can detect that they're far enough, that they've mapped far enough into the future, they have enough outstanding mapped tasks, they can also end up temporarily deactivating themselves and then reactivating themselves when they know that their child tasks have run and then therefore are no longer far enough into the future. And we'll actually, I'm not going to go into that detail today because we haven't actually looked at the task operations yet in a lot of detail. We'll be getting that hopefully next week. But effectively what we're doing is we're just controlling, each of these contexts has a mechanism for controlling whether or not they're active or not based on the number of outstanding children that they have that have already been mapped. And so that's really, they end up just calling activate and deactivate context whenever their state changes and they know they're either far enough into the future or not far enough into the future. Okay, so let's actually jump back here. I'm actually going to jump back to the scheduler now because I actually want to dive into one of these calls to actually show you what the scheduler actually does to control mapping for each of these different mappers. So let's see. If I search back for, I think it was process schedule. Here we go. Process schedule requests. It actually called perform scheduling. Okay. I can type. There we go. Great. So here we are back. This is our processor manager. So if we've gotten a request to invoke the scheduler for this processor manager, effectively this low runtime processor has said, I have contexts which are ready to map. We don't have enough outstanding operations in some of our contexts. So we actually want to perform mapping operations to see if we want to map any of our subtasks. So what we're going to do is we're going to dive into this perform mapping operations. And this is actually one of the most crucial parts of the runtime. You're going to see it's a pretty complicated function, so I actually want to walk through it in some detail to actually show you how it works. Okay, perform mapping operations. So this task, or this function actually does a whole bunch of different things. And it's gonna look complicated, but we're gonna walk through it in detail here just to show you all the different things that are going on here as part of this operation. We have a couple little data structures here that we're going to use to track some either requests that the mappers are going to do, and we're also going to track which mappers still have work that they're ready to do. So the first thing we're going to do is we're going to do a big loop over all of our different mappers. So recall that these ready queues are tracked based on size, based on the number of mappers that there are. What we're going to do is we're going to loop over all of our different mappers and look at their ready queues. Well, we have a little condition here that says, if we don't actually have a mapper at this mapper ID, we can skip it. And the next thing we're going to do is we're actually going to try to figure out which tasks are ready to be mapped, or which tasks we want to expose to the mapper to actually see if they're ready if the mapper actually wants to do something with them. And one of the important details here is we actually want to capture which generations of these operations we're actually tracking. And I'll talk a little bit about why that happens a little later. So the first thing we're going to do is we're going to pull copies out of this of the pointers to these task op operations that are ready to map out of the ready queues, and we're just pulling pointers out. And the reason for this is we don't want to actually invoke the mapper while we're holding this queue lock. So what we're going to do is we're going to take the queue lock, which protects this ready queue data structure. Notice that we can take it in a slightly different mode here. One of the cool things that our auto queues or these auto locks support, which I don't think we've seen before, is that normally you just pass it the lock, and that takes the lock in an exclusive mode, which says I'm going to own the lock as soon as I get it. You can also pass it other modes to take it in and say whether or not they're exclusive or not. So in this case, because we're doing a read-only operation on this ready queue, we can actually take it in a non-exclusive mode. So we give it a mode 1, and then we say we're going to take this in non-exclusive mode. So we can support other readers who are in the same mode as mode 1. So in the high-level runtime, you'll pretty much see there's just two modes. There's mode 0 and mode 1. Mode 0 is exclusive by default, and mode 1 is always non-exclusive. I think Sean actually enforces this mode restriction from the low-level runtime's perspective. And I'm sure he'll talk about that in some more detail. Okay, so we take this queue. Yeah.
Is that one a magic number, or is that?
Yeah, it's kind of a magic number in the sense that it's not really a magic number. It's just a convention. Effectively, everywhere in the high runtime, if you use mode 0, that's by default exclusive, and the low runtime enforces that. And then mode 1 is the only other mode I use, and it means read only.
Yeah, so the rule for the shared access to locks is you only share with people who pick the same number.
Yeah.
So it's not exclusive or shared. There's going to be different pools of shared.
Okay, but there's essentially one global namespace, and you'd better know that you're picking the same number as all the other people.
If you fail to, then you just get a little bit of extra exclusion.
But if you accidentally pick the same number when you didn't and turn off exclusion,
that would be bad.
Yes, that's fair.
Yeah, but and the high-level runtime version is very simple. I only have 0 and 1, and 0 is exclusive and 1 is read-only. Okay, so we take this queue lock, and this queue lock is protecting these ready queues. And what we're going to do is we're going to pull out a copy. Effectively, we're going to pull out a copy of pointers to all of these task ops that are ready to map. So we're taking a snapshot here of all the tasks that are ready to map for this particular mapper, and we're pulling them into a local data structure, the set of visible tasks, and we're also recording their generations. And again, I'll talk about why we need that later, but that's really all we're doing here. We're just pulling these out. We're taking a little snapshot of all the operations that are ready to be mapped and pulling them into a local data structure. Okay. I do a little bit of stomping on the C++ type system here to coerce the type into a list of task stars instead of task op stars. And the reason for this is we actually need to call the mapper with a list of task stars. And it turns out that task op stars are always task stars. And so this coercion is perfectly fine. And so what we're doing is just, getting a reference to that so we can pass it to our mapper. Okay, so now we've got a little snapshot of all the tasks that are ready to map. Let's actually do our mapper call to actually see whether or not it actually is ready to perform the mapping or see which tasks it actually wants to map here. And actually, I'm noticing a bug here, which is we don't have the proper wrapping around this mapper call to actually handle things like sending messages and other things. And so I will have to fix that later. But the first thing that we do here is we take our mapper lock. Remember that every time we do a mapper call, we need to hold the mapper lock because we want to make sure that all mapper calls are serialized to the mappers, so we don't need to worry about people writing thread-safe mappers. So we take our mapper lock. This is one of the important reasons, that we've done this snapshotting here, is that so we don't have to hold this Q lock and this mapper out lock at the same time. So what we do is, if we don't have any visible tasks, or if we have any tasks, we can skip this call if our list is empty. But in most cases, it's not. So we actually end up doing this mapper call and passing in our list of ready tasks, which are tasks that are ready to map. And so this ends up going straight to the select task to schedule. This is the select task to schedule mapper call. This invokes the virtual method on the mapper object, and you see this come out the other side, asking you when to actually pick out the tasks to map. And so this is the main thing that we're doing here. And so the mapper will go through this list and it will annotate which tasks it wants to schedule by setting that schedule field on the task object to true. And if we're going to see any of those, then we're going to actually want to do something with those. Okay, there's some other cases here. One of the other things that we're going to do is, pretty much whenever we're going to do the select task to schedule call, if stealing is enabled for the runtime, one of the things we also do is we're going to do the separate mapper call and ask the mapper if it wants to try to steal any tasks from anywhere else. And the reason for this is, we actually already have, this is the right time for the mappers to actually be making this decision. If they notice they don't have enough work, or they want to actually increase their amount of work that they have, we can actually ask them whether or not they want to continue, or if they want to make any steal requests. We have a separate lock for tracking stealing. I'm going to try not to get into stealing too much today, but just to give you a little bit of an idea of what's actually going on here, what we do is we pull out a list of we keep track of which nodes we've already sent, or which processors we've already sent steal request to from this mapper ID. And we mark this as a blacklist, which tells the mapper, hey, you shouldn't be trying to do any steal requests from this guy because we're going to ignore them because we've already got outstanding steal requests there. And so we pass in a set of steal targets and a blacklist telling the mapper what to ignore. And then we go through and when we get back the result, we process it and filter out. We're filtering out all the blacklist processors here and then tracking which ones we actually want to try to do steals from right here. Okay, and when we're done here, once we're done with doing these two mapper calls, you can see the scope here goes out of scope. We're going to release this mapper lock, which is going to, we're going to release the mapper lock, which will allow other mapper calls to be done. And then we're going to go and try and process these lists of ready tasks that the mapper may have updated. Okay, so I'm scrolling down here. We're now ready to process the results of the mapper call to see what the mapper actually wants us to do with all these different tasks that it may have marked are ready to map. Okay, at this point, we actually do need to take the lock again. So we need to take the Q lock because we're actually going to try to mutate this Q. So note that, that one and false, the non-exclusive stuff is all gone. We actually want to hold the exclusive Q lock because we actually are going to be mutating this data structure. Okay, so we're going to iterate over our list of what we were calling visible tasks, the tasks that were ready to be mapped, the snapshot that we took. And what we're going to do is the first thing we do is we're going to check to see if the mapper set this to say that this task should now be scheduled, or actually do the mapping for this task so it's ready to be mapped and run on this processor. The other thing to check, this is another field that the mapper can actually change in this mapper call, is it can actually change the target processor field on the actual task object. And if it changes the target processor from our current local processor, the processor that this processor manager is managing, then we need to send that task to whatever this new target processor is. Effectively, the mapper has asked us to send this task to a new location so it can be mapped over there. So if either one of these two conditions are true, we're going to actually have to do a little bit of work here. Okay, now here's a little bit of a tricky case to solve, or to think about. So we have this, notice that we're iterating over our visible task, which is the snapshot of the ready queue that we took. We're now ready to actually iterate over our actual ready queue. So note this RQ here is just a reference to the ready queue for our particular mapper ID. And what we're going to do is we're actually going to try and see if our ready queue, if our operation, the task that we've been told is either ready to schedule or ready to be sent somewhere else, is still in the ready queue. So this is a kind of a tricky case. So because we took a snapshot, it's possible that some other mapper call, was invoked sometime in between when we took our snapshot and when we did our mapper invocation to ask it which task to schedule. Somebody else could have come in and done some other transformation, like calling or changing the target processor for this task, and then had that task moved out of the ready queue. So what we're doing here is we're going back through the ready queue to see whether or not this operation is still in the ready queue while we're holding the lock. Because it's possible, it could have already been removed from the ready queue and moved on, in which case we don't want to do things like duplicate sends of task operations and so forth. So what we do is we go back through this ready queue and see if we can find it. So this first test here is testing to see whether or not the operation is still in the queue. So if we find it, so we're iterating over two things here. So we have visit, which is iterating over our set of visible tasks, and then we have it, which is iterating over our actual ready queue. So if we find that we found the same operation, it's still in the queue, then we should be able to actually pull it out of the queue and actually do our operation on it, either schedule it or send it to whatever remote processor we want to send it to. There's a very tricky case here that you have to pay attention to. So one of the interesting things, and we're going to talk about why this is at a later date, but operations actually are recycled, including tasks. These task operations, the actual objects themselves are recycled, and they have different to demarcate, which generation we were tracking. And so this is where we need this visible generation IDX. And the reason for this is we want to make sure that the generation of the operation currently in the ready queue is the same as the one that we initially took our snapshot of. Because it's possible that our operation actually got pulled out. It might have been mapped, it may have been run, it may have been recycled and then pulled back off and reissued for a new operation, and then end up back in this ready queue all before we actually were able to get down to this part between when our snapshot was taken and when we actually are checking this condition here. So effectively, the operations object could have been recycled, and it's now in a new generation, but we might be seeing it back in the ready queue. And we want to avoid that case. Now, this case is really unlikely, but I've actually seen it happen one time. And so, once it happens one time, then that's enough to actually, try to make your code correct and not break things. So remember that we took these visible generations, just to refresh your memory. When we took our snapshot, we recorded all the generations of these operations. And because we held the lock at that point in time, we know these are the actual generations that we should be tracking. So when we get down here and we actually, where did it go? So when we get down here and we're actually checking the current generation against the visible generations, we know we're looking, if we see that they're the same value, then we know they're the right version. Okay, so if we've identified that this is the operation that we're looking for, we can pull it off the queue. We can mark that it's found. We can break out of this little inner loop over our ready queue. If we found it, then we can, remove it from our list of visible tasks. Very, very tricky condition. If we didn't find it, we remove it from our set of visible tasks, effectively the task that we're still considering. If we did find it, then we're actually going to mark that we've actually got this operation, and we can continue running. So see the visit. We can continue. We're actually going to just keep it in our list of visible tasks, and we'll process it once we release the lock. Notice here there's some more semantics that are going on involving the context state here. So because we're pulling this task off of our ready queue, we need to decrement the number of owned tasks that we have. And so we do a little bit of tracking here to decrement our own tasks. And then we check to see whether or not we want to decrement our set of active contexts. So if our state is active, but our number of owned tasks is now gone down to 0 after we've done this decrement, then we want to mark that our context is no longer active because we no longer have any owned tasks that we actually want to schedule. And this is all safe because we're holding this queue lock as part of this traversal. Okay, and the idea here is that once we're done with this loop, this whole loop here is to effectively filter out the set of visible tasks which we've been able to pull out of our ready queue, which are actually ready to have something done. The other case here is this else branch here is the case where the mapper decided not to do anything with it. This is where the mapper actually said, just leave it in my ready queue because I'm going to decide to do something later. In this case, we can also remove it from our list of things, our list of tasks in the visible, in the set of visible tasks. So this is the else branch of this condition. So if the mapper decided not to do anything, we can remove it from our list of visible tasks because we no longer need to do anything with it. Okay, when we're done with this loop, this big loop around all of our, checking all of our visible tasks inside this ready queue, we pop out of the scope, which is going to release this queue lock again, so we're no longer holding the queue lock when we go to actually process all of these tasks that the mapper has asked us to do stuff with. Okay, so that's the end of this scope right here, so we can actually pop out and release our queue lock, and now we can actually do something with all of these tasks that the mapper has asked us to do something with. Okay, so there are two things that the mapper may have wanted us to do things with. At first, it may have changed the schedule field, which marks that this task is ready to actually be scheduled on this local processor. The other thing that it may have asked us to do is may have asked us to actually send this task to another node. So that's what each one of these two things are ready for us to do. Okay, so we're gonna build up. You can see we're already getting ready to launch, some trigger tasks. We're setting up a little structure here that's sort of acting as a reusable structure for doing the trigger task ID or meta tasks. We're only filling out some of the fields. We'll fill out the actual operation field. You can see we're filling out like args.manager here, but we'll fill out like args.op a little bit later on. Okay, and we can reuse this structure across all of our different operations that we may be spawning here. Okay, so let's iterate over our set of tasks, our visible tasks. So this list now only contains tasks which the mapper has actually explicitly asked us to do something with. All the rest of them either had already been processed or the mapper asked us not to do anything with them. Okay, this test might actually be a little bit redundant from an older version of the runtime. Effectively, one of these two conditions should be true. I'll actually probably end up pulling this if condition out. It's no longer necessary. It was probably necessary in an earlier version of the runtime. Okay, we can actually mark that we're actually no longer going to have any outstanding tasks. I think I've been ignoring most of this today, so I'll go into this in detail a little bit later. The first thing we do is before we actually do a mapping operation for a task, one of the things that we ask it to do is to actually see if it wants to defer this mapping. There are a couple of reasons you might want to defer this mapping. And the main one is the case where you actually don't have the necessary physical region tree state on a remote node to actually do the mapping here locally. And I'm not going to go into detail about, we're not going to look at this defer mapping call today, but in the cases where we actually do want to defer the mapping, we get back a lull of runtime event, which gives us a time to trigger when we're actually ready to do our mapping. This wait on event that comes back here is actually going to be a no event, which means that we're ready to run it right away. If we're ready to run it right away, we fill in the op field of this args. We give it some priority based on whether or not this task is going to be run locally or not. And then what we can do is we can actually spawn. We spawn this deferred trigger task meta task onto the lull runtime with the given wait on event and the given priority for this particular task. Just to give you a little bit of intuition about what's going on here, we give a slight edge in priority to tasks that are being sent remotely, just to get them in flight, because we want to send them off so that some other processor somewhere else can actually start processing. So we give them a little bit higher priority if we want to actually get things moving. You'll notice also that we give a little bit of priority. This is priority 1 versus the default priority 0 to these trigger tasks, because we know that once we invoke this trigger task ID, we're going to map that operation right away, and it's going to be ready to run. We actually want that to sort of jump the loop to the head of the lull runtime utility processor, so that we can actually get more tasks in flight for the lull runtime to actually see more operations and get farther ahead. Okay. Let's see. I'm just checking the rest of these conditions. I'm making sure I'm not missing something here. Right, I think in all cases we always hit this if condition, and I can actually remove this. And the rest of this here used to be in the cases where we didn't map right away. It used to be that this defer mapping could actually fail, in which case we would want to put something back on the mapping queue. But I think we've actually fixed that case now, and so this case is actually unnecessary. This is all dead code here, because we always hit this biz scheduled or target process not equal to local process or local proc. Just to show you where this comes out, where this high-level runtime trigger task ID comes out, if we search for high-level trigger task ID, okay, what you can see here is that we end up calling, so this is where we pop out inside of our meta task. We get our set of trigger task args. We get our task op that is ready to run. We call trigger execution. And it returns whether or not it's successfully mapped. This trigger execution call always returns a Boolean marking whether or not we successfully executed the task, effectively mapped it, and launched it onto the local runtime. If we failed in any way, if we didn't, map and execute this task properly, what we do is we actually end up putting it back onto the processor manager. So we can pull the processor manager out of our args and add it back to the ready queue. And note that this is we pass in true, saying we've actually failed to map this operation one time. So this add, we've come full circle today. This add to ready queue was the call that we initially started looking at. You can actually see where it comes back around in the case where we actually did fail. One detail, one important thing to realize here, and this is an important aspect of Legion that we tried to design the system with intentionally, is that Legion is designed to be able to handle a lot of these operations that fail to do things. So, failing to map or failing to execute are all important details that, most people, if things don't work, most code is written in a way that if it doesn't work the first time, you're pretty much, screwed. Whereas in the Legion case, we try to make it tolerant to these kinds of things, because when you're running into the future doing deferred execution, it's often possible that you get far enough ahead that, you run out of resources, or in the case of, say, speculation or whatever, you speculated too far into the future, things start, needing to fail and fault and recover from misspeculation and so forth. And so we try to design a lot of our operations so that we can tolerate things like failing to map and so forth. And so this is a great example, because we're, in the case where we don't actually succeed in mapping, this trigger execution call knows how to unwind itself and undo all of its mappings and then return the map as false, and then we can put it back on the things that are on the ready queue of all the things that are ready to map. Okay, so just to jump back to our processor manager, let's see if there's anything else worth talking about in the little bit of time we have left for today. Add to ready queue is where we started today. Let's see. Maybe the other thing that I should talk about briefly is checking to see which, I believe that if we, actually, let's go back to process mapping requests. Or was it perform mapping operations? So we have this one, let's see, this is going to be a little ad hoc because I'm trying to remember. Ah, yes, I remember what this is. So maybe the one thing to do in the remaining 8 minutes that we have today is just to talk briefly while we were here today. We actually looked a little bit at some of the stealing work. You noticed that we sent steal requests to actually say send steal requests. And actually, let me just show you where that actually takes place. So notice that we record which stealing targets we have for this particular mapper. So if we scroll down here a little bit, yes, here we go. So you see there are two things that are going on here. We actually track, remember that we were recording which mappers sent steal requests. So up here we have a little multi-map of processors, mapping from processors to the set of mapper IDs that, the mappers that requested steal requests go to these processors. So that's what these stealing targets are here. And we're also tracking the set of mappers that actually have tasks which are ready to map. And you're going to see both of these have to do with stealing. So the stealing targets field is getting filled in here. We're actually tracking, if a mapper requests that we should send a steal request to a certain processor, we're adding it to the list of, or this multi-map of processor and mapper IDs. And the idea here is we're going to aggregate up all the mappers that send steal requests to the same processor. And then the other thing that we're tracking is which mappers actually have work to do. So note that, here on our last pass over the ready queue, while we're holding the lock, we're still holding the ready queue lock here. Right here is if our ready queue is not empty for this particular mapper, we record that this is a mapper that still has tasks which are ready to map. And the reason that we're going to record this is we're actually going to send 2 different kinds of messages out for stealing based on the things that the mapper actually requested. So stealing is not disabled, and we actually have mappers with work. One of the things we're going to do is we're going to walk over these mappers with work and issue advertisements to all the people that tried to steal from these mappers before, but weren't able to steal because they ran out of work to do. So whenever you try to steal from a task, Legion adds you to whenever you send a steal request, Legion adds that processor that you sent a steal request for a particular mapper to a blacklist. And what that means is that we can't keep sending. We want to prevent people from shooting themselves in their foot by keep sending, tons and tons of requests for steals to mappers that don't actually have work to do. So we end up blacklisting those if steal requests fail because they didn't have any work to do. Well, this is the return part of that, which is if you've gotten a steal request from someone and you didn't have any work to do, so you had to reject their steal request, we remember that. And when we remember that, what we do is the next time we get work to do, and we actually have some pending tasks that are ready to map, but we haven't actually mapped them yet in our ready queue, we will send advertisements back to the people who tried to steal from us but failed because we didn't have anything to do before. So this is effectively announcing, hey, I've got work to do again, so remove me from your blacklist and you can send steal requests back here again. And so it's effectively just a way of preventing mappers from completely shooting themselves in the foot and making sure that we only send advertisements when there's actual work to do, and we remember when there's not work to do, but then we advertise when there's. That's what this part of tracking which mappers have work to do. We issue advertisements back to all the people or all the mappers that tried to steal from us before that didn't succeed. You can actually see this issue advertisements call is actually right here, and you'll see we keep a set of failed thieves that have tried to steal from us in the past. That didn't succeed, and we can send messages back to them marking that we've actually have work to do again. And then the other call that we have to do here is if we have any stealing targets in that multi-map that we tracked of all the processors that we had wanted to send steal requests to and all the mappers that wanted to do steal requests to each processor, we actually want to send out messages to do steal requests. So if we actually look at send steal requests, I think we've got just a couple minutes here left. What we're going to see is that, let's make sure that it's getting sent to the runtime. The runtime is packaging all these up inside of a message. So we have these serializer objects. So what we're doing is we're serializing our target processor. We're serializing the thief, the effectively who sent us the steal request in the first place, or who's trying to steal. That's us in this particular node. And then what we do is we package up all the mapper IDs that want to actually send steal requests, and then notice we invoke the message manager to actually do send the message to actually do the steal. Notice this is one of those examples where we actually have to ask the message manager to flush the message to send it right away, so it doesn't get deferred. One of the other cool things that can actually happen is that we actually notice that we only need to send messages to processors that we've requested to steal from that are not inside of our local node. So this finder checks to see if the target that we're trying to steal from is in our set of processor managers. These are our set of our local processors. If it's actually inside of our set of local processors, then we can just send that steal request directly to those processors because it's within the same local address space. So we jumped into a little bit of the stealing, but just enough to give you a little bit of an insight because we're in the same part in perform mapping requests. But hopefully, today at the end of today, you actually have a little bit of a feel for how the scheduling process actually works for Legion, how we actually control how far into the future we end up mapping tasks, and how the mapper can control that based on its mapping calls. One important thing, just to comment on before I finish for today, and that is that while I call it a scheduler, it's not really a scheduler in the sense that most people think of a scheduler. So if you'll notice that really all the scheduler is doing is controlling which tasks get mapped at which time. We haven't actually said anything about what order tasks actually run in or what order operations actually get done. And that's intentional. In fact, that's actually up to the low-level runtime to actually decide what order operations are run in based on the order in which events are triggering and so forth. And this is really the cool thing about Legion is that we don't have to make those scheduling decisions. Effectively, we can defer all those operations and let the low-level runtime deal with it so that we can automatically hide latency and stuff. And the order in which these tasks and operations map is actually not as critical as it would be in a normal task scheduler. And the reason for that is that, again, we're doing all this deferred execution so that just because we map and issue stuff in one order doesn't mean that the low-level runtime is actually going to run things in that order. So while ordering can matter for some of the scheduling process, it's unlikely to matter in most cases. And so, there's a lot of leeway here in the scheduler to actually do things out of order and do things in suboptimal orders. And the latency and cost of some of that is really being hidden by the runtime, by the deferred execution model that we have in Legion. So while I call it the scheduler here, make sure that you keep in mind that doesn't necessarily mean that it's a scheduler in the normal sense of the word. It's really just the schedule and the order in which these operations and tasks are being mapped and launched onto the low-level runtime. And the real schedule will be determined by the low-level runtime. Okay, so with that, I think we're out of time for today. I think Sean will be back on Monday to give his next low-level runtime session. And then I will be back next week. And what I think we're going to do is actually jump more into actual tasks and how actual tasks work, because they're a little bit more sophisticated than some of the operations that we were looking at in the past few weeks. So with that, if anyone has any questions, I'll take them now. Otherwise, I think we're done for today. No questions? All right, I think we're done.